Have you ever wondered how applications like Chrome, VS Code, Instagram, or even ChatGPT actually runs on hardware? And more importantly, why do we even have programming languages like C, C++, Java, Python, or hundreds of others? And what's happening between the software applications and hardware components? Well, by end of this video, you will find the answers to all these questions. Trust me, once you understand this process, you will never look at the software development the same way again. So let's begin. Imagine I ask you to write a simple program that prints hello world. In Java, it's just a few lines. In Python, even fewer. And in modern languages, writing a loop, creating objects, calling libraries, or connecting to databases feels almost like writing English. But here is the interesting question. If CPUs only understand binary, then why are we writing English like code? Why doesn't the processor simply execute Java or Python directly? The answer is simple. Because humans and computers speak completely different languages. We think using words, computer think using electrical signals, and someone has to translate between them. That's exactly why programming languages exist. Let's go back in time for a second. In the early days of computing, people programmed computers using pure machine code. A program literally looked like thousands of zeros and ones. Now imagine building an operating system or a bank application or a game using only this. One wrong bit and your entire program behaves differently. Writing software this way wasn't just difficult, it was a nightmare. So engineers came up with something better called assembly language. Instead of writing long binary numbers, they introduced short human readable instructions like move, add, sub, jump. Much easier than binary, but still every instruction was tightly coupled to the processor. If you wanted to write a simple for loop, you had to manually write multiple assembly instructions. Move data, compare values, increment registers, jump back and repeat. Something that takes just one line in a modern language could easily take 5, 10, or even more assembly language instructions. Imagine building an entire e-commerce application like Amazon or a social media platform like Instagram completely in assembly. I honestly can't imagine a software engineer spending their entire career writing software like that. And that's exactly where high-level programming languages changed everything. Languages like C, C++, Java, Python, C Sharp, and many other languages allow us to describe what we want computer to do instead of worrying about how every individual CPU instruction should execute. For example, look at this simple loop. For int I equals 0, I less than 5, I plus plus. Most developers understand this instantly. It's clean, readable, and almost feels like reading English. But underneath, the computer has absolutely no idea what a for loop is. It doesn't know what a variable is, it doesn't know what an object is, it doesn't even know what Java or Python is. To the processor, none of these concepts exist. All it understands are tiny instructions like move this value, add these numbers, compare these registers, jump to another instruction, that's it. So somewhere our beautiful high-level code must be translated into something the CPU can actually execute. Now we know why programming languages exist, but here is the next interesting question. How does this Java, Python, or C++ code actually become something that the CPU can understand? Well, there are multiple stages involved before application ever reaches the hardware. And this is where different programming languages start to differ from each other. Imagine you are writing an application in Java, Python, or C++. At this stage, it's nothing more than a plain text files. The CPU cannot execute these files directly. They first need to be translated into a format that the computer understands. This translation is performed by compilers, interpreters, or virtual machines, depending on the programming language. For example, languages like C, C++ are compiled directly into machine code that is specific to your processor architecture. Languages like Java first compiles your source code into an intermediate format called bytecode. This bytecode is platform independent, meaning the same program can run on Windows, Linux, or macOS without changing your source code. When you execute program, the JVM converts the bytecode into native machine instructions for your processor. Python follows a slightly different approach. That's where every programming language has its own execution architecture. Now here is another interesting component. Suppose you write something as simple as printf hello world. Have you ever wondered where is the implementation of printf? You certainly didn't write it inside your application. The compiler only knows that you are calling a function named printf. The actual implementation lives inside the C standard library. This is where linker comes into the picture. Its job is to connect your application references with the actual implementation present inside the libraries and combine everything into the final executable. Without the linker, your program would know what to call, but not where that function actually exists. The same concept applies to thousands of predefined functions, libraries, and packages that we use every day. Finally, after compilation and linking are complete, your application is transformed into an executable format. At this point, it contains machine instructions, references to required libraries, metadata, and an entry point that tells the operating system where execution should begin. But here is the important part. Even though your application is executable, it still isn't running. It's simply sitting on your SSD or hard drive waiting to be launched. So what happens the moment you double click your application? How does it move from permanent storage into CPU? This is where the operating system takes complete control. Your operating system is responsible for loading your application into memory, managing CPU time, creating processes and thread, scheduling tasks, and much more. In short, it manages almost everything required to run your program efficiently. But here is a surprising fact that many developers don't know. Your application never directly accesses the physical RAM. Instead, it works with something called virtual memory. Every process is given its own virtual address space, making the program believe it owns a continuous block of memory. Behind the scenes, the operating system maintains page tables, and the CPU memory management unit translate these virtual addresses into actual physical RAM addresses. This layer of abstraction improves security, process isolation, and efficient memory management. Now your executable file is loaded from your hard drive into RAM. But why can't the CPU execute it directly from the hard drive? The reason is speed. Modern CPUs operate at billions of clock cycles per second. Even today's faster SSDs have much higher latency compared to RAM. Another important reason is that RAM is volatile memory. Applications constantly modify variables, create objects, and store temporary results while they are running. Using a temporary work memory makes these operations extremely fast. I have already made a dedicated video on what happens if we replace RAM with hard drive in computer. I'll leave it in cards and description. Do check it out after this. Now our application is loaded into RAM. The operating system has done its job. So how does the CPU actually execute our program? The answer lies in something called the instruction cycle. Every modern CPU follows the same 4 steps: fetch, decode, execute, write back. This cycle repeats billions of times every second. Let's understand what happens in each step. The CPU first fetches the next instruction from memory. But how does it know which instruction to fetch? Using a special register called the program counter. The program counter always holds the address of the next instruction to execute. The CPU reads that instruction, and once it's fetched, the program counter is updated to point to the following instruction. The fetched instruction is now decoded by CPU's control unit. The CPU determines what operation needs to be performed. For example, is it a add instruction, a move instruction, a comparison, or a jump instruction? The processor now knows exactly what action to perform. Now the instruction is executed. Arithmetic operations like addition, subtraction, multiplication, and logical operations are performed by arithmetic logical unit. For example, here the CPU loads the value 5 into RAX register, adds 10, and stores the result. This entire sequence happens in just a few CPU cycles. Finally, the result is written back. Depending on the instructions, it may be stored in a CPU register, cache memory, or RAM. Then the program counter moves to the next instruction, and the entire cycle starts again. This happens billions of times every second while your application is running. So now you have seen how the CPU executes instructions. But here is the biggest question of all. How does an add instruction actually add two numbers? How does a processor compare values? How does it make decisions? Is there a tiny person sitting inside the CPU doing all these calculations? Not at all. Everything ultimately comes down to one tiny electronic component called transistor. Let's go one level deeper. So now we have reached the deepest layer of computing. We know the CPU execute instructions, but what actually performs those calculations? When I say CPU, I am actually referring to a processor made up of several important components like control unit, arithmetic logic unit, registers, memory management unit. All these components have their own specific responsibilities to do. And here is the interesting part, how these components are made with. You might have heard about logic gates if you have studied digital electronics. These are the fundamental building blocks of every processor. Basic gates like AND, OR, NOT, XOR, or others take binary inputs, zeros and ones, and produce binary outputs. By combining millions and billions of these tiny logic gates, engineers build larger digital circuits such as multiplexers, adders, subtractors, comparators, decoders, and many other components. These circuits are what actually perform the calculations needed to execute your software. But here is the final question. How are these logic gates are built? The answer is transistors. A transistor is a tiny semiconductor device that acts like an electronic switch. It controls the flow of electricity by either allowing current to pass or blocking it. That's all it does. But this tiny invention completely transformed modern computing. If high-level programming languages made software engineers more productive, then transistors made modern computers possible. Honestly, I can't even imagine today's technology without them. Processors today contain billions of these microscopic transistors, all switching on and off billions of times every second. Now let's connect everything together. Electrical voltage flows through transistors. Transistors combine to form logic gates. Logic gates combine to build digital circuits. Digital circuits become components like the ALU registers, cache controllers, and other CPU units. These components execute machine instructions. These instructions come from your compiled application, and that application started as just few lines of Java, Python, C++, or any other high-level language written by a software engineer. Think about that journey for a second. A few lines of human-readable code transformed into machine instructions, executed by billions of transistors, simply by controlling the flow of electricity. To me, that's one of the most fascinating engineering achievements in human history. If you enjoyed this deep dive into how software actually runs on hardware, make sure to check out my other videos where I explain CPU hierarchy, loops inside the CPU, USB data transfer, networking fundamentals, AI systems, and many more core computer science concepts. I'll see you in the next one.